Very good. Good evening, ladies and gentlemen, hams of all style. Bill Ragsdale here with your lesson 2 of the repeater course. This time we're going to cover components and functions. So this evening, what you will get, we're going to cover each component of a repeater. Last week we outlined them, and today we'll go to one level deeper in them. We'll go over what each component does, the characteristics, and why it's important to the operation of the repeater. And next week we'll go into test equipment and how to measure these key characteristics. The session will probably go 45 minutes or maybe a little bit less, and then we'll have time for a roundtable or a conversation or questions after that. The quick outline for what we'll see today is equipment mounting and layout, the settings for the repeater itself, the functions of a controller, ideas on feed lines and cabling, antennas, the cavity filters in some detail, the operating power for the station, and some more that fits in. The last session we had last week, managing a ham repeater, is now posted at YouTube on my channel, K6KN Space Bill. And today, again, the topic is components and functions. Next week, January 24th, it'll be tests and test equipment. January 31st, it's measurements and adjustments. And then finally, on February 7th, it'll be diagnostics. And then after that, we have a hands-on training. So a little bit of housekeeping to get started.
Notifications, Castro Valley, no traffic. He's got a conflict with a video training session tonight, so he's unable to. 860 Whitecliff.
All right, we'll try to silence that.
CES, He's of November 6th, Delta Echo Sierra, Castro Valley, 2 notifications, no traffic.
Okay, we have a little pause here while I mute a few people. I have to mute all. That's really good. Okay, folks, we're back to it. But in all modesty, I just want to disclaim and say I only know what I know. And I think probably some of the people here know a good bit more about repeaters than I do. I think I can cover about 70% of it. And maybe through the wisdom of other people, we can do a little bit better than that. We'll have the question period at the end, and so please don't do questions or interrupts during the session. And we haven't sent it out yet, but you're all going to receive an access link to our Slack site where we will do the postings of the PDFs, and you can answer questions. If you go to barkradio.org training, if you have not done so already, you can register for Slack. I'm pretty sure all the people here have already done that registration. Be sure to change your Slack settings to receive notices. If you don't receive notices, when new material is posted, you'll never know about it, and people forget to come back and see what's happened. And again, the slides will be posted on Slack. Here's a little checkup. We had a requested for homework last time, and that was that you download a data sheet for a repeater cavity filter and get familiar with that. And then the second item was that you download and review the data sheet for VHF antenna. We will touch on these 2 topics today, and it's nice if you've had a chance to see what they look like in real life on the data sheets. A couple of key terms that I'll use through the session. The COS is the carrier operated squelch. This is the sensitivity of your receiver to mute and unmute based on received carrier. So normally it is silenced until it sees received carrier and it unsquelches. However, it could unsquelch due to noise or interference or possibly even another repeater site. So it's the added element then is the CTCSS. It's a big long term, which means the continuous tone coded squelch system. And Motorola world, it's called PL. Motorola is possessive of that term and doesn't like us to use it, so we use CTCSS. So when both things happen, when the carrier operated squelch is active and then the tone comes in, the repeater unmutes and is in full operation. Another fairly technical term is SYNAD. This is a signal against noise and distortion. This is used for testing the repeater, for setting squelch level, for checking against descends, and we'll talk more about it in the next two sessions. The method is that an otherwise unmodulated carrier, a 1 kilohertz tone is added and then going through test equipment and analyzed, and the comparison is made between that tone and the noise to evaluate the repeater characteristics. The key elements in your repeater, if you either manage one now or if you're examining what other people are doing, of course, there are a number of locations. You can have a rooftop antenna. In that case, your area coverage is maybe 4 or 5 miles. If you have a tower 20, 30, 40 feet up in the air, you might get 9, 10, 12, 14 miles. If you get 300 feet up in the air, there's a repeater at UC Davis that's up on the top of about a 5-story building, and that would qualify. You get about 20 miles. But to get true coverage, you need a high-level repeater, and the BARC, the Mount Vaca repeater, and the N6 ICW are all at 3,000 feet, which get very good coverage. You have the decision to make of one antenna or two. One antenna, I believe, is the most common because it only costs you one antenna. And if you're on a tower that is populated with other antennas, you might be fighting for space. However, a 2-antenna system relieves a lot of the technical limits because you get much better isolation between your transmit and receive side. And the BARC repeater is a 2-antenna style. Another component of the repeater is its internal control. You either have an integrated controller that's built right into the repeater box, or you might have a separate controller. We'll talk about both. Another issue is coordination. I assume that all the people here today are using repeaters that are coordinated. Those are the standard, useful, long-term repeaters. An uncoordinated repeater is generally somebody working from rooftop, doing it from home for fun. And it's really essential to have website support for a repeater so people can find out your frequencies, your offset, and get a little bit of background on it, find the PL tone. At repeaterbuilder.com, there is a huge checklist on repeater decisions. There's about 50 items on their checklist. It is exhausting. It's exhausting just to read it. Repeater-Builder is an excellent site. It is sort of the Wikipedia of the repeater technology. A few standards that should be applied. The first one is power connections. The Anderson power pole, I believe, is becoming the de facto standard. There is what's called the ARES standard, and this is how they clip together. There's 2 ways to clip them together, and if you put them in the proper orientation, your connector will plug into commercial power supplies, and if you're doing field work, you can easily go from power source to power source. Second element that's quite important is that for RF connectors, they should be silver plated and not chrome or nickel. You want to avoid dissimilar metal. You can get detection and images and irritations that will pop up if you have dissimilar metals in contact. So RF connectors should be all silver plated. And the RF connector type should either be the N connector for your transmit and receive pathways, and either N or BNC for test leads inside the vault. The UHF connector should be considered as dead. It is not dead, but all VHF and UH work should be using the N connector. The UHF connector was never designed for good radio characteristics. It was designed based on its mechanical ruggedness. A few technical operational standards. One is that you shouldn't really use any adapters for professional installation. This means that cables should be fitted with the proper mating connector for whatever they connect to. Bureau of Land Management actually specifies no adapters. on the sites that occupy a BLM site. And again, this is to minimize any cross modulation or interference problems. We'll mention this several times, but in your cables, you should not use any foil braid combinations unless there is a barrier between the two. The LMR series, for example, is the biggest offender of this. We will see one LMR series cable that does have the insulation barrier. And again, cables are discussed in great detail at repeaterbuilder.com. At rfindustries.com, they have an exhaustive catalog of connectors, fittings, cables. It's a gold mine of information there. It's a nice little educational source as well as shopping list. We'll pull up again the view that we had of the overall station that we're all quite familiar with, where we have the receive antenna feeding through an input receive filter. Receiver demodulates the audio, that remodulates the transmitter. The RF goes up to the transmit filter and out the transmit antenna. At the bottom, we have the power supply of AC utility power, batteries, and solar. So let's talk about mounting. Two general styles of mounting. The most industrial is the rack mounting. These are 19-inch relay racks developed in about the 1920s for telephone industry use and have been adopted throughout technology ever since. They are a denser form. If you're having multiple repeaters in one location, this is the way to go. The access is a little more difficult. You either need to be able to walk around behind the rack or you need to put things on a shelf so you can get access to the back. The alternative is tabletop. This gives you easy access but low space utilization. The Bark repeater has some, about 12 feet of bench space, and so all of our equipment is plunked along across the benches. So now we'll talk about the repeater itself. First, this is a huge topic. We can only touch on the top elements. We won't be able to go in and compare one unit against another. That is better off done on some of the websites where you can read all the details. Current practice regards these as what you would call a black box. The controls are on the front panel and you do not open the box. There are no internal adjustments, no screwdrivers needed. And if you have a problem you can't cure from the front panel, then you return to factory. Most of these have an internal controller and offer an external option. There'll be a connector on the back that can plug in an external controller. Let's talk about time generations. What I'm calling first generation would be from the 1960s, 50s, 60s, 70s. These were repeaters that had limited front panel and you had to open them up and make the adjustment with screwdrivers, or they used a code plug. The code plug is either a chip, a connector, or a programming method where you use an external computer to set your characteristics. This is done more in the industrial setting where you had portable field radios, mobile radios, and they don't have a front panel on them for technical use. You have to put the code plug in to make all the adjustments. The second generation came along probably in the 90s, early 2000s. LCDs became quite popular. Most of the repeaters in this time period then had an LCD text display and a simple keypad on the front. So you could, the measurements you used to have to do with test equipment and using a screwdriver on the inside, you now do through the display. Our Bridgecom is an example of that. Probably about 8 years ago, the industry transitioned to a color graphic touch display. We're familiar with the Yaesu type. Almost all their full line of radios and repeaters as touch screens, and it's pretty well the standard through the industry. The methods of input and control, as I mentioned, the first is just entries from the front panel with a keypad and a display. The second is by a computer link. Often these are proprietary. You have to get the software from the manufacturer and the connector from the manufacturer, but it enables records to be kept. You can do a setup of the repeater, copy the setup file, and if you ever have to reload, you've got the setup done immediately. And the last choice is remote programming over the air. And again, from about 1995 onward, repeaters generally were equipped with on-air programming. There's a wide range of capability in all of this programming styles. You need to check out for any repeater you're interested in, find out what its resources are, and do some comparison shopping. Let's examine the construction level and the design of individual repeaters. What I'm calling ham grade are the ones that are designed mostly for radio amateur use. The most familiar is ICOM, Kenwood, and Yaesu. These are the big three. There are several more, and Bridgecom is one of the, shall we say, lesser names in that bunch. ICOM, Kenwood, and Yaesu are selling to a worldwide market, and Bridgecom is selling just to a domestic US market. Then there is the industrial governmental market. And to my knowledge, Motorola is the big gun in this area. I'm not familiar with enough of the vendors to know if Motorola has any significant competition, but for almost all in your government military work, you're going to find it's Motorola. There is a lot of it in use, though, in the ham world, because Motorola equipment taken out of service can be repurposed from commercial service into radio amateur use. And you'll see some of the most well-organized and comprehensive repeaters in this area are done out of Motorola. And very often, the ham that's managing these is doing governmental work where they learn their training. So settings, the key three settings on the repeater, as we would expect, is the transmit receive frequency, the receive frequency, and the power level. These again are set conveniently from the front panel. The receive and transmit frequency very often are factory set to when you buy a repeater, but easily changeable in the field. And the power level, likewise, some have 2 or 3 or 4 power level steps. Our Bridgecom has continuously variable power level. The squelch, carrier operated squelch, is a little more involved. Bridgecom gives some guidelines on setting it without test equipment. It's much better to set it using the SYNAD method, which we'll talk about in future sessions. The CTCS is a simple setting. It is just a single frequency, click taken off of a menu. It's always should be used at on the receive side, and sometimes it's used on the transmit side, and either with the same or a different tone frequency. By having it on the transmit side, it allows you to mute your equipment in case, unless you are on that specific repeater. These days, there is a move toward digital repeaters, and the digital repeaters don't have that output tone ability, and so you can use that to separate a digital from non-digital. Final adjustment is the hang time after the carrier drops. Usually it's 1 to 2 seconds after the carrier drops. If another user comes on stream within that time period, the carrier does not drop. Otherwise, after about 2 seconds, the carrier drops. In that case, you get a couple of clicks. The repeaters, as we know, are required to identify at least at 10 minutes intervals. And so you often have a setting for 10 minutes or less. And they often will ID at 8 minutes because they want to be under that 10-minute limit. Also, they'll all identify by CW, and some controllers will identify by voice. The final technical element is the bandwidth or deviation, which is set by the audio gain. And again, this is a front panel setting. One way to set the bandwidth is by using the word for. That's the F-O-U-R word, for, and you say that word over, increasing the deviation until you hit a distortion, then back off a little bit. That's a very crude way to set it, but the other methods of using test equipment is much, much better. The Bridgecom give some seat of the pants ways to set that modulation level. The controller again, which is internal to the repeater, you might think it sits between the receive and the transmit side. It does the integration. It's a simple microprocessor that integrates the COS, CT, CSS, the timeout, and the identification. Again, a lot of repeaters allow you to put an external controller on. The controller can be integrated or add on. In our Bridgecom repeater, it's internal, and in our Maggiore repeater, it's an external unit. Most often, I think these days it should be considered automatically that you will have remote control via touchtone. So you can come in with the proper security controls and make changes to the repeater, and particularly being able to mute the repeater in case of malicious interference. Some installations put a backdoor link into the repeater so you can make settings via external data link. More secure, better control. Some repeaters are multi-port. There are 2-port and I think 4 or 5 or more port controllers. This allows you to integrate on one unit multiple repeaters. It is common to have a VHF and UHF repeater at the same site, sharing the same information, and then you have a 2-port repeater that connects them. Or the other way is the second port could be going to a control link. Let's talk about cabling. We've mentioned before, no braid foil combinations unless they're isolated by a foil layer. We want all RF links to be double shielded or heliax. The problem is that braid insulated cables only shield about 90%, sometimes less than that. So it means you then can have unintended RF floating around the shack, cross connection possibly between 2 cables. If you have cables for an extended run parallel to one another, you can have crosstalk between them. So it's essential that the RF cables be double shielded or heliax. Now, heliax is a corrugated copper long tube, corrugated, wrinkled so that you can bend it, and it's solid copper, so there is no leakage from heliax. You often hear the term hardline to say, oh yeah, we have a hardline installed. Well, it's a little bit of a misnomer. A hardline is actually a coax cable made out of a stiff copper tubing with a center conductor and insulators. And so it is as stiff as a copper pipe, and difficult to bend, difficult to manage. And so a hardline really is not used in ham operations. It might be used industrially. I suspect it's cheaper than heliax, but you have the problem of mounting it and bending it. Finally, all of these double shielded industrial style cables need special tools, especially the end connectors. Again, we'll review for outside cable that should be double shielded or heliax. One example is Andrew. They own the name Heliax. They have a division called CommScope. Pasternak does sell an LMR 400 DB version, and that is the dual insulated. It's got the foil and the braid, but with an insulating layer between. For interconnecting cables, that is within your vault, a very highly recommended version is the Andrew 1/4-inch Superflex. Again, these coaxes should be shielded. There's a sequence there, the RG214, 142, RG393, 400, and so on. All are double shielded. They have various diameters of various bend radiuses. You need to be careful. Some of them have a bend radius limited to 4 inches. Some have a bend radius of 1 inch or so. For test leads, these should be small and flexible, and the RG400 or the RG214 qualify. They are double shielded, and often you can find them on eBay. They're a little pricey. New, I believe they run about $3 a foot, and on eBay you can find them because they have been repurposed from some aviation uses. And you can generally find 20 to 27 foot links reasonably priced to make your test leads out of. Warnings from repeaterbuilder.com. Don't use Belden 9913. It has water sensitivity. And as we said repeatedly, no LMR 400. So we've come down from the antenna, we come down through the cabling, and now we're at the edge of the vault. So here's the ideal place to put transient suppressors. Now, we hesitate to call them lightning suppressors because they will not stand a direct lightning strike. If you have a direct lightning strike to the tower, it likely will take out the antennas, a chunk of the feed line, and if you are lucky, it will not get into the shack. The goal is that the suppressor is sacrificed to keep the energy out of the shack. There are several technologies that are used. The gas tube, I believe, is the most common. There are some that are solid state. They mount on an outside wall, as you see here. I look at this. This is our installation. I look at the ground lead on this, and I do think that looks a little inadequate, but I would rather see some 1-inch braid going down to the ground on that. Some of them have replaceable elements, so that if you've had either repeated static discharges or possibly a lightning discharge in the neighborhood, and you've had a breakdown in some of them, they have an air gap or the gas tube may be damaged. And so they have a little lifesaver size disc. You unscrew a cap, take the element out, put a new element in. One of the complications is that some levels of technology of transient suppressors have an air gap. So normally you would expect you could do a continuity measure from through your cable to your antenna. An interesting trick is to, on your antenna, put a high value resistor across the active to the ground, something like a 1 megohm resistor. This allows you to measure continuity by simply putting an ohm meter on the input in the shack side, and you can measure that 1 megohm resistor up in the air. And of course, the 1 megohm will have no interaction at all with your RF and will absorb no power and can be a low wattage rating. But if you use that method and you have an air gap in your transient suppressors, you do not get the continuity measurement. So it's just a matter, it's not a real problem. You just need to know what the characteristic is. So for antennas, the introduction, there are no magic answers. There is no best antenna. There are multiple trade-offs based on economy, durability, mounting style, wind resistance, the gain, and so on. The question I've mentioned before is one antenna or two. One antenna is most economical when you've got only one feed line going up and you have a minimum tower space. But for two antennas, if you have them 10 feet apart vertically, you get 35 dB of isolation between them. That's a 2,000 to 1 reduction in crosstalk, and this makes life very much easier. For about 40 years, our repeater had what I regard as inadequate cavity filters, and the saving grace was the 35 dB of attenuation because the antennas were separated. You have a choice of your mounting. It could be a simple pole mount on a rooftop, a tall building, possibly a tower, and then you have the issue of guide versus unguide. It depends on the height of the tower, its construction style, and in particular the base. I'm not an expert on this, but I think if you are on a concrete pad, you would definitely have a guide tower. If you have a deep concrete base, then you can go unguide. And the Bark repeater is an unguide tower because the fellows who put it in back in the 90s dug about a 5-foot hole into some deep rock and poured it full of concrete. And so they've got that tower well secured. The antennas have the characteristic of gain. Now, the antennas don't really electrically add any power, but what they do is they direct the radiation. Instead of going up and down, they direct some of it, and more of it in a horizontal fashion. The theoretical antenna is a point source radiating in all directions, so-called isotropic antenna, which does not occur in reality. Real antennas deviate to some degree from that isotropic configuration, and that is called the gain. So if you have a 1 dB improvement over that mathematical isotropic form, you say I have a 1 dB gain of antenna. What it means is the energy that will be going up and down is directed more horizontally. The typical antenna of a quarter wave, the gain may be 2 to 3 dB. We use an extended length antenna that's about 9 feet long, and this gives us about 4 to 5 dB of gain. That is significant because 4 dB is more than doubling your radiated signal level. If we have a 60-watt transmitter out, the effective signal that gets into the air is closer to 100 watts. It's advantageous to favor the receiving side. If you're going to spend time, money, elevation, or quality, put it on the receive side. In our case, our receive antenna is at the top of the tower, getting the greatest clearance from the ground. I'm not sure, since we're at 3,000 feet, if another 70 feet matters or not, but we do have the receive side high. The reason for this is that the repeater transmit power is far and away higher than what the people in the field are using. And likewise, the antenna is much more efficient. If you've got a handy-talkie sitting 50 miles away, you've got a little whip antenna that's 6 to 10 inches long and maybe transmitting 4 or 5 watts. So what is important is that the repeater is able to hear that weak signal far away, because the chance is extremely good the person in the field is always going to be able to hear the repeater. So put the money on the receiving side. Here's a couple of examples of the antennas. There are two major technologies that are used. On the left, we see the ground plane antenna. On the right is the folded dipole. The ground plane has a vertical and then some sort of horizontal components that add the ground plane portion. You can see this is our antenna. It's quite long. As I said, it's about 9 feet long. The folded dipole on the right is another style. They often are done as either as a single loop or 2 loops, or in this case, 4 loops. The greater number of loops is the more horizontal is the beam pattern and the better antenna gain. There's a major cost difference between the two. Our consumer level diamond antennas are about $125, and the folded dipole on the right is about $800 to $900. However, if you're in for the long haul, you really want to go for the folded dipole. As you can see, it's all metal construction, very much more rugged than the ground plane type antenna. Cavity filters. They're a set it and forget it. Once you set the cavity filters up, unless you've had a severe lightning strike, you forget them forever. We've had some filters in that have been from the 1970s and are still a perfect condition. On the top left, we see the passband characteristics of the bandpass filter. The multiple red lines are from an adjustment, so you can set the degree of sharpness. The narrower the bandwidth, the more loss that the cavity has. So you have a compromise between how much bandwidth you want on the side skirts versus how much loss you want in the cavity. In practice, you would then lay the charts side by side of the transmit and receive filters so that you want a minimum crossover between the two. The chart at the bottom left is the notch filter. And you can see they are quite sharp. There's some 40 degree dB attenuation at the notch frequency. They are significantly sharper than the receive side. Generally, you would have 2 bandpass filters and one notch filter, the typical sequence for one antenna. On the right-hand side, we see a section view of them, and we see that the cavity is nothing more than a can. You probably are familiar with the tune circuit, where you have an inductor and a capacitor together. Well, amazingly, the cavity filter is the equivalent of a tuned circuit. The upper and bottom plates of this are the equivalent of the capacitor plates, and the circular can around the outside is the equivalent of the inductor. It is a one-turn inductor. So set up on the inside of that can are circulating currents at your RF frequency. Because these are carrying RF frequencies, the inside surface is generally silver plated. The cavity is tuned grossly by its dimensions, and then in a fine way by the tuning knob and the bar that's called a resonator. And one of the tricks on this is that you need frequency compensation. As the cavity changes dimensions, its center frequency will shift slightly. So they use a special alloy metal for that bar down from the tuning knob in, called INVAR. And it has an equal and opposite expansion characteristic as the to the copper. So it will maintain your tuning over a temperature range. The top you see on the input connectors, just below that are the coupling loops. Those coupling loops are rotated, and that sets the bandwidth and the loss. Again, one-time settings, set it and forget it. This is an example of using a one antenna system. The label at the top is wrong. It's a one antenna, not two antenna. So you see the top diagram has a transmitter going out through two cavities, then the receiver going out through two cavities to an antenna on the left. It doesn't show any notch cavity. And a somewhat more complex arrangement down at the bottom. And at the left, we see the transmitter goes to an isolation coupler, then LPO is the low pass filter, BP is a band pass filter, then up through it's just to the baiting of the two together to the antenna. On the receive side, it shows an optional bandpass cavity. Of course, we're going to have a bandpass cavity there, and most likely a notch filter too. So you see, there's a little bit more complications when you go to a one antenna system. So the key parameters for the filter, and these are how they're purchased. One is the physical size, does it fit? But secondly is the bandwidth and the loss. The larger the physical dimensions, the lower loss and the narrower the bandwidth. So you get onto, say, Telewave's site, you start looking at data sheets, and you start swapping between different versions. There are generally three major designs. There's the bandpass and the reject, as we've seen. And then Telewave does offer a pass reject, where both are in the same can, and they have a dual set of adjustments. The common setting is to have two pass filters and one reject. If you're operating at particularly high level, or for some reason you are not operating on ham frequencies, if your transmit receiver offset were narrower, you might have more cavities. The isolator is a two-port method. It allows RF to go through in one direction. Circulator is a point where you mate the receive and transmit antennas together to a single port. This is a bit of black art in radio, because these isolators are done by very powerful permanent magnets. And when the radio waves pass through the permanent magnetic field, they actually bend. We won't get into that. There is very good detail on this at the ARRL antenna book, chapter 17. At the end, we'll have references that you can copy down. So how to measure operating power? Most of the ham repeaters, I believe, operate somewhere between about 40 watts and possibly 100, maybe 120. But the ones I seem to go between 40 and 80 watts. And it's good for your operating power, your AC power. I am very stuck on AC supplies that have meters because you can do quick diagnostics by looking at the meter. There are two styles, linear and switching. The linears are the older style. They have more magnetic material, more iron in them, bulkier, run a little warmer, but they are electrically quiet, non-noise generating. The older switching supplies had a bad reputation of being noise generating, but the FCC now is so firm on emissions from devices, noise-making emissions such as switching power supplies, that I think switching is every bit as good now in linear for ham use. It's essential that you have a battery operation. We scope them out at about 5 days capacity because the rule of thumb is that utility power might be down for 3 days at a time. And we'll talk a little bit about that in a moment. And solar these days is so economical that it's really important that you have solar panels on top so they can keep the battery charged if you lose utility power for an extended period of time. Connectors, we mentioned the power pole a moment ago. Older installations might use Molex, but from a ham use, that's pretty obsolete. They are not as rugged as the power pole, harder to get hold of, and not nearly as easy to troubleshoot. We'll see in a moment photos of the EPIC power gate and a brownout protection unit. These were used, we saw these last week. And finally, grounding comes along. This is a big topic. There are various schools of thought on how to ground and what should be grounded. In general, the bigger and wider, flatter copper, the better. The closer to a ground field outside, better. But the only detail we go into here is to see the ARRL Handbook for Radio Communications on chapter 28, and they will get you started on the issues on grounding. These are typical photos. Upper section is a Astron switching power supply, 25 amp power supply with meters. The bottom left is the EPIC power gate. This is the heart of a power distribution system. It is really a wonderful piece of equipment because you plug into your battery, your AC power, and your solar, and this keeps the battery charged. It does no break power to the repeater, and it even has the diagnostic lights will tell you what's going on. There is a little button on the left that says do not push, because you push that button and you go into a special charge cycle for 30 minutes, and then you think something is malfunctioning and you're in a charge cycle. So they caution you, only push the button if you know what you're doing. By using the power pole connectors on here, we're able to plug and unplug these for testing the individual components. On the right is a brownout protection. When the DC voltage drops below about 11 volts, it will cleanly break power to the repeater and will keep the repeater unpowered until the power recovers to a given threshold above the dropout point. We were having some lockup problems on the repeater, and we put this in, and we think it has been beneficial. So here's a worst case story. This is what can happen with power. About 2 years ago, PG&E went down. There was extended weather. They let us know that it was going to be down for an extended period of time because at the mountaintop, they could not get physical access to that area because of the road conditions. And a lot of what they were doing was off-road, and they literally couldn't physically get up the hill. So they said, you're on your own. It turns out the power was out for 10 days, and most of this time it was raining. Well, we estimate that we can get about 5 days on battery operating fully for a normal schedule. And with the solar add-on, we were able to get we'd get to a total of 9 days because it was raining. And under sun conditions, with 4 or 5 hours of sunlight a day, we could do full operation. But we were operating at what we think was 30% of solar capacity because of the continued rain. So we went down after 9 days and we're down for about 15 hours. The sun came out, and in 4 hours of sunlight, we're back on the air. So this shows you worst case situation, the dependency that you have on utility power and coordinating all of the elements of your power system. So a few irritations and discoveries that I've made along the way. You will discover your own. It's essential you keep a notebook, write everything down, because you will come back months later and try to make comparisons and figure out what happened. So keep that notebook up to date. Some of the discoveries I've had is we have a DR1X, which is a analog digital repeater. And as we were about to put it into service, we've realized it had no remote control or mute. There was no way to silence this repeater other than physically cycling the power or turning it off. Well, for us, that's a 2-hour round trip up the hill, and it was not feasible that we could accept the operation with no remote control. I believe they have newer models now that have the remote control. We haven't investigated that. Another difficulty is the fan always runs. Now, I know fans are reliable. It may get 5 years, 10 years, but sometime along the way, the fan is either going to get dust accumulation or bearings go out and you lose the fan. Now you have a repeater with no fan, and you have no indication if it's going to overheat or not. So the fan should always be on at either a timer to be tripped by transmit operation or temperature operated, because if it's temperature operated, you should have a fan that has indefinite life, years and years. Also on the DRX1, the early models would lock up, and that was another reason that we did not put it into service. The current Bridgecom BCR50V, one of my irritations is the poor manual. There are 2 omissions in the manual that because of that, we had to send it back to the factory. And then we found out that if the information had been in the manual, we would not have had to do that. It also has limited remote control. We can mute it remotely, but that's about all. And it's locked up a couple times, and they claim that that's been fixed. And we hope it has. Another discovery, our old original repeater from 1995, the Maggiore company, was a couple of hams working out of a small shop, had a beautiful design, rock solid, all transistor, crystal filters, beautiful design. I loved it. It was in service for 28 years, but the company went out of business. And so now we're orphaned. And so we bought another repeater and we use the Maggiore as backup. Another difficulty, the controller that we added to the Maggiore was the computer automation CAT 250, which I love. It's a great controller. And guess what? That company's out of business. So I make the general observation that the industrial-oriented firms stay in business longer than smaller ham-oriented business. These are the ICOMs and the Yaesus, and so on, the Motorola's, the ones that are selling to a broad market and that are international, not just a specialty company run by some hams, are more likely to stay in business. I regard MFJ as a notable exception. They are an excellent company, great support, great product breadth, and I'm sure they're going to be around for a long time. So next week, here's what we'll see. We're going to cover test and test equipment, your record keeping, the essential test equipment you must have, would like to have equipment, setup details, antenna tests, power supply, and simple remote tests. It's how can you use digital voltmeter, power meter, antenna analyzer to do your basic tests. The session after that, we'll do deeper technical work. So your assignment for next time is find a way to buy a Bird watt meter. I'm not saying go buy it, but just find out where you could get one and how much they cost. The older Model 43 is the workhorse. That's the one that I own. You can generally find them on eBay. The newer model is the 4410 series. It is more streamlined. It appears to be physically the same, but it's an updated version, and it's at an updated price. And for that, you will need what they call the plug-in element, which the hams call a slug. It's a cylinder that plugs in, and it sets the power level and the frequency range. So you need a 100-watt VHF slug. They're again available typically about $80 on the used market. Try new or used, try eBay, look at some of the ham sites like eham.com and so on. While you're at it, go to the birdrf.com site and look at the full line, because they have a very, very broad line of RF-oriented test equipment. There will be an evaluation form posted at our Slack support site. I don't have it up there yet, but once I get that posted, please fill it out to let me know how I'm doing. And here are our references for this week. The first is the registration, which most of you have already done, and then the address for the Slack site. But once you register, you'll be able to log on to that. And our videos are posted at YouTube on K6KN Bill. Be sure to go by Repeater Builder. As I said, it is the Wikipedia for ham radios. It covers about everything. And it's essential that all hams should have the ARRL Handbook for Radio Communication and the ARRL Antenna Book. So that covers it for this week. We thank you for your rapt attention, and we will stop the ceremonial recorder.